Um, okay. So I'll have the talk proceed in 3 sections. First will be some sort of intro, background section, then motivation for topology, and then I'll call it, I don't know, just direct presentation of topology. Okay, so let's start the first section, intro. Before we talk about topology, we need to talk about sets. Sets are the object, the sort of fundamental object that's used in most of mathematics. So what is a set? Well, I won't try to define it too precisely in this lecture. We'll treat it sort of a little looser. A set is just a set of things, right? So we will visualize that by, say you have a bunch of things, mathematical objects, points, numbers. A set is just you take some of them and you put a box around them. And that's your set. Or at least that's how you should visualize sets. We do this a little bit more formally usually by specifying which elements we have in the set. So for example, if I consider this set over here, it has all of these things, and how I would write that down mathematically is if I look at, say, the number 1, 1 is in this set, I would just write 1 is an element of this set S, if S is this box. So that's pretty straightforward. Often when we're defining sets, we don't literally draw the box. It's usually easier to list all the elements that are in a particular set. For example, if I wanted to write this box, I could just write it as curly braces 1, 2. So you just write curly braces, and then in between the curly braces, you either list all of the elements or some way of specifying a bunch of elements that go into that set. Okay. Now that we know what sets are, let's see what we can do with them. So the one most important thing we do with sets is ask whether one set is a subset of another set. So that leads us to our first definition of the lecture. So a lot of math is about definitions. So we're going to define what a subset is. So if I have two sets, A and B, or sorry, A and X, let's say, we say that A is a subset of X, which we write using this symbol. A is a subset of X. By definition, if every element of A is an element of X. This does not go the other way around. It doesn't mean that every element of X is an element of A. If that's the case, if they have all the same elements, then they're just the same set, they're equal. But here we only require that if it's in A, then it's in X. So as an example, this set is a subset of this set because this only has these two elements which are both in here. Okay. So I already gave you one example, but I want to give you another example. And I'll give you an example of a set. Actually, I want to talk about kind of the most important set, which is something called the empty set. And the empty set, which we usually write like this, is the set with no elements. So in this sort of pictorial way, you can picture it as just an empty box with nothing in it. Now, it seems kind of trivial or maybe pointless to have a set with no elements in it. But actually, the empty set is very nice. It's the only set that we can write down without knowing anything else. So I don't have to know about numbers or stuff like that. It's just a set with no elements. And it has an interesting property, which I'll note here, which is that for any set X, the empty set is always a subset of X. Why? Well, let's just look at the definition. Every element of the empty set is an element of X. Why? Well, because there are no elements of the empty set. So all 0 of them are elements of X. Kind of a trivial statement, but fun to think about. And it will be important later. Okay. So now that we have sets out of the way, well, one more thing about sets, which is I want to tell you how we manipulate sets, or the two sort of main manipulations that we'll need to know. And you've probably heard of them before. This is the idea of the union and intersection of sets. This is so this might be known, but I'm not sure. And we'll take a more general approach than is sometimes done. So the idea is as follows. So I mentioned that, or did I mention? Okay, well, I want to mention that the elements of sets can themselves be sets. In fact, this is very often the case. So if I have a bunch of sets, A, B, C, and maybe more, and these are all sets, so they're all boxes in their own right, but then I can draw a box around all of them and construct a new set, and this is a set of sets. Now, if I have such a set of sets, then there's two operations I can do. There's the union, which we write like this, and we define like this. The definition is the union is the set. I'll again use curly brackets, and then I'll specify all the elements. It's all elements that are elements of A or elements of B or elements of C or etc. So an element of the union is an element the union contains all the elements from any of the sets. Then the other thing that we can write down, you can probably guess, the intersection, is basically the same thing, except we change the or here to and. So instead of being inclusive with our elements, we're exclusive. So all elements that are elements of A and elements of B and elements of C, and so on and so forth. So to be in the intersection, an element must be an element of all of these, A, B, and C. To be in the union, it only needs to be in one, at least one. Okay. Yeah. So is that clear? I think, because then we're going to move on to maps. So what are maps? Well, this is not enough to do mathematics as we want to do it. We want to do more than just collect things. We also want to have some idea of doing like computations, right? So that's where maps come in. So, so what are maps? Well, like I said, we want to do some kind of computation. So, um, so rather than just collecting elements, we want to collect. We want to have collect elements, do something to them, and maybe dump them into another set. So maps go between two sets. Maps are also sometimes called functions, and I will call them that as well. Usually, function has, if you're talking about functions, you're thinking about numbers, but not always. And more generally, we just call them maps. So a map is, again, between two sets. So let's say I have two sets here, x and y. And a map is just a way of assigning elements in y for each element in x. This is supposed to capture doing some kind of computation, kind of. So let's take this example where I have these sets here, set x, which is 1, 2, 3, y, which has star, triangle, circle. And so we visualize, just like we visualize the sets as boxes, we visualize the maps as arrows that point from the elements of one set to the elements of the other set. So we need one arrow for each thing in here. So this would be an example. This collection of arrows would be an example of a map. And just like we give sets letters to give them names, so we talk about them, we can do the same for the functions. So this collection of arrows here I could call f. F then denotes our function. And typically we write this little bit of scribbles just so that we can indicate in one statement that f is a function that maps, or it's a map that maps the set x to the set y. All right. Okay. So that's what a function is. How do we use functions and how do we define functions in practice? Well, there's one other bit of notation to introduce, which is the idea, which is essentially, again, the function as a whole is this collection of all the arrows. But what we may want to do is we may want to look at a specific point in here and say, where does it go, right? Do the computation for number 1. And so this is evaluating this function at a point. And with the notation we use for that is we use these round brackets. So for example, in this case, if I want to evaluate this f at the number 1, I will just get this star here. And so this is the function evaluated at a point notation. And this is also very useful for defining functions. We can define a function just by specifying where each point maps to, rather than drawing this picture. All right. So now let's, just like we had a simple example for sets, let's go over a simple example for functions. I mean, we had this example, but let's do a trivial example. So given any random, any arbitrary set x, we talk about something called the identity map or identity function, which we write like this. And this is a function from the set to itself. So here, x and y are the same. They're just x. There's no problems there. And this is defined very simply. It's again kind of the only thing you can write down without knowing anything else about x, which is that we define this such that for all little x in capital X, if we evaluate this function at that point, little x, it just gives me back little x. All right. Simple example. And the last thing to finish off functions is to talk about manipulation we do with functions. Oops. And in particular, we talked about subsets, right? So now we have maps and we know what subsets are. How do these interplay? Okay. You know. All right. How do these interplay? Well, if I have some function from set x to set y, map from set x to set y, and then I have some subset. For example, let's start with, let's say I have a subset of the thing we're mapping from. I have a subset of x. Then there's a very natural subset of y that we can write down, which is just essentially where all of these points map to. And this is where all of the points in A map to. So this is what we would call the image of this subset A under the map F. And this is exactly what I said in words. This is the set of all elements in Y. So it's going to be a subset of Y, but it's not all elements in Y. It's only those that get mapped to by an element of A. Pretty straightforward. For example, here, if my subset A was just the set 1, 2, this is A, well, we only look at those two elements, and we look at all of the things that they map to in here. So the image under F of that A is just going to be the set containing that 1 star element. Okay. Okay, so we could do essentially the exact same thing if we start with the subset of Y, except we do it in the reverse order. So we call it the pre-image instead of the image. Pre-image under F of some subset of Y, B, is exactly analogous. It's just all elements in X which map to something in B, or an element of B. So again, going back to this example, it's just the same example. The pre-image of this set would be this subset. Pretty simple. All right. And that sort of concludes the review, more or less. So any questions on review of set theory and maps? All right. Whoops. So at this point, one thing I want to stress, I guess, is that although I've been using numbers and these points, right? There's at this level, there's no difference between numbers and these other symbols I wrote down. Um, they're all just points and sets, or sorry, they're all just elements of sets, right? Um, if we're just dealing with set theory, we don't have any sort of extra structure, then there's no difference between numbers and these other random points I wrote down. What makes numbers numbers is all the extra structure that they have, that you can count. You can add numbers and get other numbers and so on. That's what makes them numbers. So we really, going forward, we need to talk about adding extra structure to these sets. And that's precisely what topology is an example of. So typically in mathematics, we will add extra structures to sets, and that will make some sort of whole branch of mathematics depending on what kind of structure we add. So if we add a group structure, then it's group theory, whatever that is, and so forth. And we'll talk about what a topology is that we can add. It's extra structure. And that's the general scheme. So now let's talk about topology. So the point we're going for with this whole subject is we want to talk about continuity. So topology is all about continuity. It's a way of formalizing what continuity is, and we'll start by sort of leaning on some of your intuition for what continuous functions are. So what is okay? So maybe some of you probably have if you sort of look up the word topology and you on YouTube or something, you'll find examples of topology has to do with that donuts are the same as coffee mugs, right? Well, the idea there is again still continuity. The idea is that you can have different shapes, right? A donut and a coffee mug, but one can be continuously deformed into the other. And to make that precise, you need some precise notion of continuity. You need to study topology. Okay. So to introduce continuity, I'll sort of lean on your intuition of real numbers and the number lines from pre-calculus and go from there. So this is the second section, motivation. Let's go over. No, this is good, I think. So we'll start with a special case, a very special case, where we consider maps that go from the real numbers to the real numbers. So this big R is the real numbers, just the numbers you're familiar with, 1 pi square root of 2, blah, blah. And we can visualize the real numbers on a numbered line, which we draw like this. 0 might be over here, 1 is over here, something like that. And if we have some function from the real numbers to the real numbers, we can visualize that by just plotting the graph on 2 number lines stacked up like this. For example, I will draw one example. This is the graph of some function. So on the x-axis is some dummy variable u, and then on the y-axis, on this axis, we will plot the function evaluated at that u. Now, the example I drew here looks continuous, at least according to our intuition. So let's draw a different example which doesn't look continuous, just a contrast. So maybe I'll draw something like this. So here, what's the difference here? Well, the difference between this and this looks discontinuous, but how do we sort of capture that? Well, what we captured here is that this jumps some non-zero amount, arbitrarily quickly. It just jumps by some non-zero amount. And if we want to talk about how we would start formalizing this, right? What we can say is that if we look at this particular point where it jumps, x, the function at that point evaluates to f of x. If we look at some interval around f of x, we can choose a small interval that's smaller than this jump size because it jumps by some non-zero amount. And if we choose that interval, which we could say is of size epsilon, around f of x, then as long as epsilon is smaller than this jump, then there's no way to get the values of the function completely within this interval by just zooming in around this point over here. You can zoom in as much as you want, but you're always going to pick up part of this branch where it jumps discontinuously, and you will never get all your values to be within this interval. Okay. This is not the case here. Here, if I take any point, right, then no matter how small intervals I choose around it, I can always zoom in such that, it doesn't jump. Okay, so let's take that intuition. We can't just work with that as it is. If we want to write proofs or something, we have to state things out a little bit more precisely. But if you kind of follow this intuition, you'll pretty naturally, with some experience, that's the caveat, be led to the following definition, which is called the epsilon-delta definition of continuity for real numbers. So the definition is as follows. A function f from R to R is continuous by definition if the following. So this is going to be long. Just try to follow it as best as you can, but again, without experience, this is quite long. But it goes like this: for all x in the real numbers, for all small parameters epsilon greater than 0, there exists some small parameter delta greater. There exists some delta greater than 0, such that for all u in the real numbers, the absolute value of x minus u being less than delta implies that the absolute value of f of x minus f of u is less than epsilon. So again, very long and not really digestible unless you, again, just go through this example and think of how you would precisely state this out in like full logic. But everyone's comfortable at least with like absolute values of real numbers and everything, I'm assuming, pre-calculus. So uh, so this is a perfectly okay. So I mean, this definition has pros and cons, right? The pro is that it does somewhat follow from these pictures, but the con is that it's very long and complicated. And it has another con that we'll get to in a second. But this is the starting point of our motivation. Now we need to think about how we would generalize this, because at the moment we're only talking about real numbers. While I'm erasing the board, try to read that like 5 times. I guess that wasn't enough time, but you know. Okay. How do we generalize this? Again, we want this to apply. We want to be able to. We want to be able to talk about continuity if I have a function from any x to any y, where these are not necessarily the real numbers. But if these are just sets with no extra structure, we can't do that. There is no notion of continuity for a function between sets with no extra structure because there's nothing else you can write down. There's no extra structure. So we need to provide some extra structure to these sets such that we can talk about continuity. And we want to do that in kind of the minimal way. The one sort of natural starting point is to just look at that definition and to recognize that the absolute value of difference between two real numbers. If you look at this on the number line, this is just the distance between those two numbers on the number line, right? So maybe the natural way to move forward is to replace this with some sort of more general notion of distance, which we could just invent some d between two elements of these other sets. Now you can do that. That seems to give us exactly what we want, right? Because we don't have this d, but if we provide this d for x and another d for y, then that's extra structure by providing a notion of distance. And so providing that extra structure, then we can talk about continuity in an analogous way. So you can do that, and that will work. It will give you something, but it doesn't quite give us what we want in the end. And the reason is a bit subtle. And the reason is essentially that you're giving too much extra structure if you specify some kind of distance. Distance is a concept from geometry that you'll remember. And so by providing some sort of d for this x, you're providing a geometrical structure for x. And then you can talk about continuity, but that's actually more than we need. You're providing extra structure that you don't need. So how do I illustrate that? So for example, I could start with some x, and then I could imagine giving two different geometries to x, d and d prime. And these different geometries can have very different geometric properties. For example, with one of them, it could be triangles will work differently than with the other, something like that. Or one of them, x might be finite in size, and the other one it's infinite in size. So they could have wildly different geometric properties, and yet still be such that, regardless of whether I use d or d prime, if I try to parrot this argument, it won't matter which I choose. The functions that are continuous or not will not change. So the question of continuity is independent of which of these wildly different geometries I choose. So if I only care about continuity, I want to do, then I'm led towards topology, which is a bit of a weaker structure. So one way I can visualize that is, I have my bare sets here. And then in mathematics, we want to add extra structure, and sometimes this is pictured as sort of stacking things on the sets. For example, if I want to do number theory, I would start with my sets, and then I would add number theory by adding, extra structure like addition and multiplication and these kind of things. Here I can do geometry by adding extra structure. I can do geometry by adding, distance functions, maybe something having to do with angles and other things, straight lines. But because with vastly different geometries, I can still have the same set of continuous functions. What I actually want to do is have a slightly weaker structure, which we call a topology, which sort of fits in between here. To fix this problem of the redundancy from the point of view of continuity, the redundancy of different geometries. And this other structural layer is what we call topology. So that's where it fits into this tower between geometry and pure set theory. But okay, so that's nice. That's kind of a target, but how do we actually do that? Well, there's a trick, and I'll just tell you the trick. The trick is to look at something called, or is to look at open sets. Open sets are something you're probably also familiar with from the real numbers. So let's talk about open sets of real numbers for a moment. Excellent. Okay. So open sets of real numbers. Let's imagine I have a open subset of real numbers. So let's say I have a real number line, right? A subset of the real numbers is just picking certain points on that number line. One example of a subset is the set of all real numbers that are between 0 and 1. Or say, so greater than 0 and less than 1. Which on the number line would look like this open interval. So you would have all these points between 0 and 1, but you would not include the endpoints because I did not put an equal sign. So you kind of have a line segment, but you don't include the endpoints, right? Now, another subset of the real numbers I could put down is I could make this less than or equal to, and then I would include the endpoints and have some sort of closed interval. I can also do half open and stuff like that. But I really care more about the open intervals. And in particular, we don't have to consider just one interval. We can consider an open set where essentially I can have points in some sort of bulk area of the real numbers, but I never include a boundary point. And if I never include a boundary point, then my subset of the real numbers is open. Okay. So, but how do I, now I have to do kind of the same thing here. How do I talk about not including a boundary point in a precise way? Well, it turns out the definition for how you would do that looks a lot like this epsilon-delta definition of continuity here. So let's just do that. We can actually sort of deliberately make it parrot this definition. We can define the notion of open set of real numbers. In exactly the same way, except we say a set, a subset of the real numbers, is open if, and then we write some sort of analogous things for all x in A, for all epsilon, small parameters epsilon greater than 0, there exists delta greater than 0, such that for all u in the real numbers, absolute value x minus u less than delta implies, did I mess this up? Yeah, this is kind of pointless. Sorry about that. You know. So we don't have to worry about that epsilon, but you can imagine, yeah. So for all x in epsilon A, there exists delta greater than 0, such that for all u, yes. So actually, it doesn't look exactly like that. There's no epsilon, but it's a similar style. You know, you have to deal with these deltas and this absolute value of x minus u. Okay. Okay. So it's just, you know, some. So this now this actually completely solves our problem because this has the same this has the same type of redundancy that I was talking about earlier, in that if I were to try to mimic this definition, but with some more general notion of distance, then I could have different geometries which have completely different geometric properties, but they would have the same open sets, just like the same functions would be continuous, right? And in exactly the same way and for exactly the same reason. So this kind of gives us a hint that really we should be focusing on the open sets. And it turns out you can rewrite the definition. You can have an equivalent condition for the continuity of a function that only depends on the open sets and not on any kind of geometry that it comes from. And so that's the motivation for focusing on the open sets being how we construct this lower level structure, this weaker structure that we call a topology. So that's the motivation. Focus on the open sets. And that's the end of the motivation section. So now let's just do the topology. You know. I'm going to keep the, actually, it's probably not worth keeping this. Again, don't worry too much if you don't digest these. These are very long definitions. Oh, one of the advantages of doing this is not only do we get this, this sort of neat minimal structure, the topology structure is also very simple, and the definitions are much simpler than dealing with these epsilons and deltas. So that's just a nice bonus. All right. Oh, I'm kind of running out of time. But now let me just say that now that we are talking about topology, we can do it in one line. I can say topology is the study of topological spaces. And now all I have to do is define what a topological space is. So definition. Again, the motivation here is we want to focus on the open sets. So a topological space is two things. It's your set. These are the x's and y's you wanted to give extra structure, and then we give extra structure to it. And that extra structure is called a topology. And together they form a topological space. So where this extra structure that we're giving it is a specification of which sets we want to consider open. So what this is mathematically is this is a set. O is a set. It's a set that contains sets. It's a set that contains subsets of this X. So where O is a set containing subsets of X. So it doesn't have to contain all subsets of X, right? But it can contain all subsets of X, but it doesn't have to. And it's just some choice of subsets of X. And that choice of subsets of X is the extra structure. Making that choice is like choosing a specific type of distance. It's an extra structure. But it's not just, we can't just choose any random subsets of X and have an easy time. We won't be able to prove the things we want to prove, and it won't really capture our notions of continuity. So we require that that this O satisfies three properties, and these properties are called the axioms of topology. They're three simple properties. They're properties that, if I talk about open sets using this definition in the real numbers, they're properties that open sets of the real numbers have. And they're really all the properties you need to prove the things you want to prove about continuous functions. I can't show you that here. You just have to take a full topology course and convince yourself of that. There's really nothing else you want to write down. So I'll just write them down for you. So the property one is that the empty set, okay, it's coming up again, and the total set are elements of topology. So actually, let's write it like this. The empty set is an element of the topology, and the total space. Topology. So for the empty set to be an element of the topology, that means it has to be a subset of X. But we already showed, that was our sort of first fun example, that it's trivially true that the empty set is a subset of any set. Okay, so that's property one. Property two is where we finally get to use unions and intersections. Okay. Sorry, wanted. All right. Property two is as follows. Let's say I have a bunch of sets that are subsets of X. And actually, let's say I have a bunch of sets which are elements of the topology. So A, B, C, blah blah blah, up to Z. These are all elements of the topology. Then, if I have such a thing, then the intersection of the set that I get by grouping all of these into one bigger set, exactly what we defined earlier, A, B, C, dot, 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 Z. This is also going to be an element of the topology. We're guaranteed that it's a subset of X just by how sets work, right? Because the elements of this are going to be elements of these, which are all elements of X, because these are all subsets of X. But it's not guaranteed in general to be back in this collection, but we require that as our second property for what we call topological space. So notice here, the most important thing is that I wrote a Z at the end. So that means I can have any number here, but it has to be finitely many. So the intersection of a set made up of finitely many open sets is open. Actually, and I want to rewrite this in a way that's a little bit neater. If all of these are elements of the topology, then that's the same as saying if I construct this set here, the set of all of them, that is a subset of the topology. Does that make sense? That's the same thing. So we can more neatly write this by saying that for any subset, of the topology, the intersection of the subset is again in the topology. But this subset here has to be finite. Alpha is finite. Okay. So that's property number two. Let me just squeeze property number three on the board, but let me maybe draw some lines so that it's clear. So this is just a rewriting, i.e. This is a rewriting of the second one in a way that's a little bit neater notation-wise. And then the third property is the same thing, but for unions, except for unions, we don't require this finiteness. So, so the last property is for any alpha subset of the topology, the union of alpha is again in the topology. So those are the axioms of topology. If I have any X and then I choose some collection of subsets. As long as they satisfy these three properties, I have what I call a topological space. Any questions on that? All right. Okay. I'm surprised there've been 0 questions, but I don't know if that's a good sign or a bad sign. Probably a bad sign. But I'll just continue going anyway, and now do some examples. So some examples of like simple things. So there's two things I want to say, and I'll give one example for each if I have time. The first is that, oh, sorry, I forgot to define what a continuous function is. That would make this whole thing rather pointless. Sorry, actually, I want this clipboard. Okay. So now, remember, this was from the motivation section. I'm just leaving it there for comparison. Now that we're just doing topology proper, I can just write a very simple definition for what a continuous function is. Again, these are continuous map, right? These are the maps that play well with this extra structure that we've given. The definition. A map F from two sets X to Y, if these sets are also topological spaces, so that this comes with a topology, and this comes with a topology, which I'll call tau for Y's topology. So these are topological spaces. A map is continuous if for all open sets in Y, or for all B open sets in Y, again, this is just terminology, are just the elements of the topology. That's what the topology does. It specifies which sets we want to consider open. So any open set in Y, its pre-image, that thing we talked about earlier, the pre-image of that open set under this map must be open. If it's not open, then it's not continuous. So there we go. That's one line, and only one for all. It's significantly neater than that definition. So that's right there is one advantage of talking about continuity and at this level rather than needing a geometry. All right. So I'm technically out of time, but for the purpose of this quiz, if you let me go over by just like a couple minutes, I will give you an example of a simple proof you can do. That way, you'll see at least one proof in the lecture. To see how you write it. Okay, so there's various properties of continuous maps that are, thanks to this simple definition, much easier to prove with this definition than with something more complicated like that. In particular, I'm going to look at one, which is the theorem that By theorem, I just mean I guess I didn't say that explicitly, some statement about your mathematical objects that you can prove. So we'll prove this theorem. For any continuous function f from x to y, and g from y to some other set z, the composition is continuous. The composition, which we write like this: G circle F, which is a map from, I will explain what this means in a moment, or how we define this. I just want to write it fully first, which is a map from X to Z is continuous. So if you start with continuous maps and you do this composition thing, what you get is still continuous. That's clearly something we want, but I haven't told you what composition is. So let's make a little aside. A cloud. This notion of composition of maps is a pretty straightforward one, and it gives us an excuse to use our notation. So we define this idea of a composition of maps by just doing the maps one after the other. So the composition, if you take in any element of capital X, is just you map that element using F to some element in capital Y, right? F of little x will give you some element of capital Y, and then you just use G to map that into Z. So you just do one after the other, do one mapping after the other. This for all x defines this composition. So now I want to prove this theorem real quick. Sorry, do I have time? Yeah, give me like 2 minutes. I don't know, maybe 3 minutes, 4 minutes. Okay. So, proof of that theorem. It works like this. Basically, so let's start with given some sort of f and g continuous. I don't have to write this out explicitly because it's kind of stated in the theorem. But yeah, so f goes from x to y and g from y to z. Then we want to show the composition is continuous, which means we need to show that the composition satisfies this definition here. So let's just start with the definition. We need for all open sets in the target, which is the one that we're mapping into, which is z, something is true. So if we need to show something is true for all open sets, we just assume we have some arbitrary open set. So let B element be an open set in the set we're mapping into, which in this case, again, we want to show G after F is continuous. So we want a set that's open in Z, we'll say it's an element of the topology of Z, let it be otherwise arbitrary. Arbitrary. If we can assume, or sorry, if we can then show what comes after it without any additional assumptions, then we're done. Okay. So the first thing to do is, what we want to show is this over here. So I'll just put this in parentheses. You don't always have to do this, but just for clarity, what we want to show is that the preimage of this composition of B is open, which means it's an element of the topology on X. So that's what we want to show. And we will show that by just noting a very simple thing from set theory. So this is why these proofs are simple. I'm running out of time, so I can't show in full detail. But basically, by drawing those arrows that I did earlier, you can pretty quickly convince yourself that if you do this whole composition thing, the preimage of the composition is just the composition of the preimages. So this is preimage under F of the preimage under G of this set B. Again, I'm running out of time, but you can draw pictures. Give me 2 more minutes and then it'll only be 10 minutes over. Now, we need to show that this is open. And it follows essentially immediately. All we have to do is note that this thing, preimage under G of B, is open, which means it's an element of the topology of Y. Why? Well, that follows from the definition of continuity, but for G. G, again, we don't need to show that G is continuous. We're given that G is continuous. So we can use the definition. B is an open set, so its preimage under G has to be open. And so we have this for free. And now, this here is some open set in Y. It's not the original B that we assumed and we let be arbitrary, but whatever it is, it's certainly an open set in Y. So we could call it C, just to call it something else. And then what we want here is actually just the preimage under F of C. That will give us what we want to show is open. But this has to be open because C is open and F is also continuous. So just one additional application of the definition, but now to F rather than G, tells you that this is an element of the topology X. So we've shown that for any arbitrary B, we can show that the preimage of that B is open. Thus, it's true for all B, and thus this map here, G after F, satisfies the definition of a continuous function. So we're done, and we can write QED if we want to get some satisfaction from having finished it. So, okay, sorry, that was way more over time than I wanted, but that's that.
Now it's just time for questions and
Question.
Why is SCP Fall a system of data that can only correlate a finite number of operands, suggesting many signs infinite?
That is a good question. So there's 2 ways to answer that, and I'll give both answers. So one, Oh yes. So the question was, why is it that in our axioms we chose we allowed arbitrary unions, but in the case of the intersections we required that they must be a finite number of them. Why didn't we write just for any arbitrary intersections? this is true. There's two answers to that, so I'll give them. One is that if you remember earlier in the talk, I defined open subsets of real numbers using this epsilon-delta type definition. That was supposed to appeal to our intuition of open sets. And if you look at those open sets of the real numbers according to that definition, then you are not guaranteed that if you intersect an infinite number of them, that it will remain open. That's just, you can come up with counterexamples in the real numbers. And so if we required that, then our original motivating example wouldn't even be a proper example of a topological space. So that's one answer. The other answer is that essentially you can imagine trying a different version of a mathematical structure where you did require that this was true for arbitrary intersections, right? And you would the normal real numbers and their notion of open sets would not be an example of this, but you could still work with it and see what sort of things you can prove, and it just wouldn't really behave in the way you expect things to behave, and you kind of just. I don't have maybe you have better exactly examples. Okay.
Right, that intersection, then that you can always choose some integer small enough so that you will have nothing contained in that intersection, because that intersection, which isn't, and maybe it's worth writing it out so people can see.
Is this an example of the real numbers things?
The intersection of the open intervals, -1/n, comma 1/n.
Oh yeah, so this would be
And you're intersecting all overall natural numbers. But that will not contain anything but zero. Zero is the only thing contained in that, but that is an intersection of open sets. And so, in other words, if you allow arbitrary intersections, then you get statements like zero is an open set, but that is completely contrary to our original notion of open set. We want to find open set the generalization of open intervals. A generalization of open sets in R. That's not an open set.
yeah. That's my that's an example of the first reason I gave, which was that this property is not true for arbitrary intersections in our motivating example of the real numbers. I don't know of a good example of if you tried to like develop the subject of topology but allowed for this, that you'd get some weird behavior, but I'm sure the answer is you would, and you kind of just have to do that. Yeah, I don't really know off the top of my head what would go wrong, but you wouldn't get the kind of behavior that you wanted. You'd either wouldn't be able to prove the kind of things you want to prove, or you would be able to prove too many things that it becomes not very useful, stuff like that. Yeah. Basically, yeah. You could probably show under some other mild assumptions that like every set has to be open, right? I think so. And then it becomes kind of useless, right? Yeah. 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 So it would become sort of just, I mean, a thing you could define, but not very useful for anything. And you kind of just have to work with it for a while to see that. I can't give one example, but you know. Anyway. Good question. Very good question. Any other questions? Yes.
Could you run us through your first example of, you have that graph that you had done, how would that translate into this line?
In that, actually, that's a good thing. good example as well. So the example with the jump motivated sort of epsilon delta definition, but now that we have this more general topological definition, can we sort of see the violation directly? And we can. If I go back to this graph, that looks like this. Let me choose the following open set in the real numbers, the following B. Let B equal basically this set, where I take an open interval around f of x, where x is where this jump happens. Okay. And B is some open interval around this f of x, right? That is smaller than the jump size. Then if I look at the pre-image under f of that B, if this was continuous, then by definition this would have to be continuous, but we immediately see that it's violated. The pre-image of this set is the set which is some sort of open interval here, but it's not an open interval, it's a half open interval. It goes up to, but it includes this point x. So the pre-image is not open. It's a half open interval, which is not an open set. This. Yes, that's a good example.